Okay, I wanted to have a quick run through this uh, turbine blade geometry. So I got this from GrabCAD, and it looks quite nice. It originally came as a solid part file, so first thing to do was to convert it to STL, which I did using Anyconv. And I like the look of this geometry because it's got the cooling holes in it. So I thought it'd be interesting to do a cooling analysis. So first thing I did was I had to extend the hub wall a little bit, and also for the cooling part I had to extend the cooling passages so that they could be at the same level as the bottom of the geometry, so that I could easily they would get um, when you do block mesh and then run snappy X mesh, then the faces here will get recognized as part of the outer boundary, and so then these become Z-min faces, and then they also have some Z-min faces either side. So then all I have to do is to separate them using topo set. Um, the other thing about this geometry, it's not really a proper cooling geometry as far as I can tell, because for a start, when I look closely, the cooling holes on this side don't even meet the cooling passage here. So this part's connected. Then also there's something a bit odd about the way this has been done. It doesn't seem very connected very well, but but extending these passages down to the Z-min surface does the job, because then you get airflow going to all of them. And despite this dodgy connection bit here, the airflow is getting through to all of the holes. So that's that. And um, looking at block mesh. Now for this case we need cyclic boundaries. So in block mesh you just select cyclic and then couple it to ymin to ymax. And then same for ymax, cyclic coupled to ymin. And that does a great job, because when you run it in Snappy Hex Mesh, it automatically creates those as cyclic boundaries, which is fantastic. Um, so that means when you go to have a look at your boundary file after Snappy's done its thing, the cyclic's all set up perfectly. So you've got a cyclic here, and ymin coupled to ymax, ymax to ymin, and then the important bit, translational connection between those surfaces, and then that's the distance between them. So with this geometry, the actual scale of the turbine blade was 1 meter, and then I scaled it down to by a factor of 10 to make it 10 centimeters. And apart from that, I need to specify Zmin, Zmax, and blade as walls. So I think I edited this file for that. And yeah, so in terms of the boundary conditions, I tend to keep those in a separate directory. Boundary conditions, because I've got a total pressure inlet, and I've used pressure directed inlet outlet velocity, which does the job. So that gives me allows me to specify the direction of the inlet, which is important for a turbine blade case. Otherwise, it will just go normal to the inlet. So no slip for the walls, and then for the cooling, I started off with the pressure inlet, but that was giving some uh, some wrong, some very high velocities at the inlet. So then I changed it to flow rate, well, to a mass flow rate. So I just calculated the approximate velocity and then worked out the mass flow rate. So I've set that at 0.02. So that works great. For the pressure, I just set a 0 gradient at the cooling inlet. Yeah, in all of the input files, you have to specify cyclic for cyclic boundaries. Yeah, for the X-min, I've just set a total pressure. Well, I guessed it really, of 150 kilopascals. So total pressure inlet, fixed value outlet, and then there's the other turbulence files and whatnot. So I haven't specified any rotation for this. It's not like one where you specify a high-speed rotation. It's literally just like a static blade with some flow going across it and then the coolant going through it. So, well, in terms of the flow solution, it ran for 3,000 iterations. When I run, I save the output file, so then I can use Python plot watcher. And so the convergence looks okay. I mean, I could run it for longer if I wanted to. I ran this in parallel on my laptop on 4 processors, but 3,000 seemed like enough because I was monitoring the maximum velocity in the flow domain. And so you can see when it starts, it goes up and hits the limiter a few times, which is okay. That's normal. So yeah, you can see here that the peak velocity goes up to 364. That seems to be nice and stable. It's the peak velocity in the flow. So that's what I monitored. So when I load the flow solution into ParaView, skip 0 time. So what it actually does, it loads up the block mesh that's in your constant polymesh directory. So that's the block mesh. Then because I meshed it quite large, then I scaled it down by a factor of 10. So if I deselect skip 0 time, then it should load in the actual mesh from SnappyXMesh, which is quite a bit smaller. So that's that. Let's deselect that. It's at 3,000. So you can see here, and we've got the cooling flows which are at 300 Kelvin, and then the exterior flows are at 400 or thereabouts. So that's all good. And we can switch that to velocity. So you can see the cooling flow is as it should be, which is quite a low velocity. Although there is a few dodgy points there, which are wrong. It seems like a slightly sensitive boundary condition, this one. So that's the mass flow rate that's been specified there. I suppose you could also try having a fixed velocity. That might be worth a try actually. Um, that's an alternative strategy, is to have a fixed velocity there if you know what velocity you want for that. So we could take a cut through this, a Z cut. Get rid of the perspective view, get rid of that plane. So this is what we're looking at halfway up the blade. So if I change the Z value a little bit, that's annoying. Yeah, if I change the Z value, then you can see the cut through the cooling holes. So this is pressure plot. So I could change that to temperature. So you can see there the mass flow rate, excuse me, is just enough to give some flow coming out of the holes there. So you can see the temperature difference, and you can go to velocity. So it's quite interesting in this case, is because so the velocity is at 45 degrees here. So this velocity in this region is about 150, but then due to the turning effect of the turbine blades, the velocity increases towards the outlet. I could do with a bit more mesh refinement here to capture the wake, but we've got flows of 350, or peak flows of 350, which actually might be occurring down here. But so yeah, you've got a significant increase in the velocity there, and you can also put on velocity vectors. Oh, if you like that way of doing it. Scale factor. That seems, that's not what I wanted to do. Let's try that again. Why? Scale array. Oh, that's it. It was the scale array that was set wrong. Solid colour on that one. So yeah, got there eventually. You can sometimes prefer to have a 2D glyph. So here you can see that the flow inlet is coming at 45 degrees, and then it's going down that way. So those arrows, I think, are on the other side of the plot. The flow must be slightly out of plane. So there's that way of looking at it, and then if we get rid of that and go back to, we can take off the internal mesh and just look at the surface. So just looking at the blade surface. So that is showing velocity. So yeah, we can see the effect of the cooling holes here, cooling the surface. So this is not a conjugate heat transfer, it's just a fluid analysis. We can see the effect of the cooling holes there. And so yeah, that's about it really. The only other thing I want to mention is the other things that I've used in this case are I use the scale command for scaling the mesh, transform point scale, so that's quite useful. if you want to change the scale of the mesh. And I also used topo set. I use this quite a lot, but in this case I've just specified a box to clip the boundary, the cooling inlet. So when you mesh this, like I mentioned, you get a Z min is um, on the bottom there, and it's also on those surfaces there. But if you specify a box that is just thin enough just to clip those boundary faces, you can do that in topo set. So just with a tolerance of plus or minus 1 millimeter to clip those faces. So you use topo set, and then you use create patch dip, and then so that changes the name of them from Zmin to cooling. So that's basically separates out the cooling surfaces. Um, so what else? I can't remember if I talked about the peak velocity in the flow. Um, plot monitor. I think I might have mentioned this. But yeah, I monitored the velocity in the flow, the peak velocity, just to keep an eye on that. So yeah, I think that's everything. So that is just a very quick run through how to do this in openfoam. This is openfoam 12, which is like the modular version of the solver. And so this is just using the standard fluid solver, which allows you to have temperature and density because it's compressible flow. So that's what was used.